Lots of scientists saying 3I Atlas is changing course after the flyby. The moment when decades of orbital mechanics expertise, when centuries of Newtonian physics, when all the elegant mathematics that lets us land robots on Mars and slingshot probes past Saturn would be validated once again by 3I Atlas following the exact path gravity dictated it must follow. Closest approach at 269 million kilometers, safe distance, no drama. Just another data point confirming that yes, we understand how objects move through space. That yes, the universe operates according to laws we've decoded. That yes, prediction and observation align because that's how science works when you do it right. Except that's not what happened, because in the days following December 19th, as tracking stations around the world continued monitoring the interstellar visitor, as position measurements accumulated and velocity calculations refined, something became undeniably clear. The trajectory wasn't following the script, wasn't staying in the narrow tube of space where gravitational models said it had to be, was deviating, not slightly, not within error margins, but measurably, repeatedly, impossibly, changing course in ways that don't just bend the rules of cometary behavior, but break them completely. And here's what makes this so disturbing. These aren't gradual drifts, aren't slow accumulations of small errors. These are episodic, sharp, distinct. The object moves along its predicted path, then boom, course change, velocity shift, directional adjustment, then it stabilizes briefly before doing it again. Step, 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 like something is firing, like thrust is being applied in bursts, like the visitor from beyond our solar system is maneuvering. If you think that sounds impossible, if your brain is immediately searching for conventional explanations because the alternative is too unsettling to contemplate, I need you to understand something. The people tracking this object are not amateurs making rookie mistakes. These are the same teams that calculate planetary positions 1,000 years into the future with precision measured in meters. The same institutions that navigate spacecraft across billions of kilometers and hit targets the size of parking lots. They don't miss. Their math doesn't fail. And right now, their math is telling them that 3I Atlas is doing something it shouldn't be able to do. Before we dive into exactly what's happening, before we examine the numbers and the implications and the uncomfortable questions this raises, do me a favor. If you want to follow this investigation as it unfolds, if you want to understand what happens when an interstellar visitor refuses to follow the laws of physics we thought were absolute, hit that like button right now. Subscribe. Turn on notifications, because what we're about to discuss isn't being covered by mainstream outlets. The data is too strange, the implications too profound. But it's real. It's documented. It's happening right now as that object speeds away from Earth toward an encounter with Jupiter that nobody can predict anymore. The foundation of everything we're about to discuss is orbital mechanics, and I know that sounds dry. I know it sounds like textbook physics that everyone assumes they understand. But bear with me, because understanding why the current situation is so impossible requires understanding how breathtakingly precise our predictions normally are. When you want to calculate where an object in space will be, you start with Newton. Gravity. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. It's elegant, it's simple, and it's been tested so thoroughly, validated so completely across every scale from falling apples to orbiting galaxies, that calling it a law rather than a theory isn't hubris. It's just accurate description of how the universe operates. You plug in the numbers, the sun's mass, the object's current position and velocity, the gravitational influences of all the planets whose masses and positions we know with absurd precision. You solve the equations, which computers do billions of times per second, and out comes a trajectory. A line through space showing exactly where the object will be at any future time you care to specify. There's uncertainty, of course. Your measurements of current position aren't perfect. Velocity has error bars. The object's mass is estimated rather than known. So the predicted trajectory isn't a single line, but a tube, a bundle of possible paths clustered tightly around the most likely trajectory. The tube is narrow, For well-observed objects, the uncertainty might be a few thousand kilometers after months of travel across billions of kilometers of space. That's the precision we're working with. That's how good the predictions are. 3I Atlas was being tracked with that kind of precision. Multiple observatories, independent measurements, cross-verification. The trajectory tube was tight. The predictions were confident. Scientists were publishing papers with projected positions months into the future, positions calculated to better accuracy than you could measure by pointing a telescope and looking because the math was that solid. And then the tube started expanding, not because measurement errors were accumulating, but because the object wasn't where the tube predicted it should be, was outside the bundle of possible trajectories, was deviating in ways that couldn't be explained by any reasonable adjustment to the gravitational models. At first, the response was standard procedure: check the observations, verify the measurements weren't artifacts or errors, confirm that multiple independent stations were seeing the same deviations. And they were. The position offsets were real, not glitches, not mistakes. Real deviations from gravitational predictions. Next step, refine the models. Maybe there's a subtle gravitational influence we underestimated. Maybe the object's mass is different than we thought, affecting how planetary gravity perturbs it. Maybe there's outgassing, the standard explanation for non-gravitational acceleration in comets, and we just need to quantify it and add it to the calculations. But here's where things get strange. Because as the tracking continued, as more deviations accumulated, the pattern became clear. And the pattern wasn't what outgassing produces, wasn't what any natural process produces. The deviations were episodic, happening in discrete events separated by periods of stable trajectory. The object would cruise along, then experience a velocity change, then cruise again. Not smooth, not continuous, pulsed. And that's not how comets work. That's not how any natural object in space works. When gas escapes from a comet, when ice sublimes and creates thrust, the process is continuous as long as the surface is heated. It might vary in intensity as the comet rotates and different regions face the sun, but that variation is smooth, predictable, tied to the rotation period in ways you can model and account for. 3I Atlas's thrust events aren't tied to rotation, aren't smooth, aren't predictable. They're happening on timescales that don't match the object's spin, in directions that change between events, with magnitudes that vary, creating trajectory deviations that compound and make long-term prediction impossible. Let me give you the numbers because precision matters when you're making claims this significant. The velocity changes, the delta V in each thrust event, are small in absolute terms, meters per second, maybe tens of meters per second at most. That's tiny, a leisurely bicycle speed, nothing dramatic. But these events are adding up. Multiple thrust pulses over days and weeks, each one slightly changing the trajectory, each one adding uncertainty to future predictions. And because we can't predict when the next thrust event will occur, or how strong it will be, or what direction it will push, the uncertainty cone grows exponentially. After a few weeks of this behavior, the region of space where the object might be has expanded from thousands of kilometers to hundreds of thousands to millions. The trajectory has gone from a tight line to a broad cone. From precise prediction to, we have no idea where this thing is going. That has never happened before with a tracked object. Never. We've lost spacecraft when communications failed. We've had asteroids disappear behind the sun and become hard to locate when they emerged. But we've never had an object that we're actively tracking, that we have good observations of, become unpredictable because it keeps changing course. And the episodic nature is what breaks all conventional explanations. Because if this were steady outgassing, if it were continuous thrust from sublimating ice, we could model it, could measure the thrust direction and magnitude, plug it into the equations, and regain predictability. But episodic thrust that varies in timing and direction and strength, there's no model for that, no way to predict the next event. No framework that accounts for pulsed acceleration that doesn't correlate with rotation or solar distance or any other measurable parameter. So scientists are left watching in real time, tracking where the object is now, documenting each thrust event as it happens, building a database of deviations, and trying to find patterns that might allow prediction. And so far, no patterns have emerged beyond the basic observation that yes, these events happen episodically, and no, we can't predict them. The outgassing explanation was the first refuge. It's what every astronomer reaches for when comets behave unexpectedly, because outgassing is real, it's measurable, it creates thrust, and we understand the physics. Ice absorbs solar energy, temperature rises, molecules gain enough energy to break free from the solid lattice. Gas expands rapidly into the vacuum of space, and as it expands, as molecules shoot away from the surface, Newton's third law applies. For every action, an equal and opposite reaction. The departing gas pushes the comet in the opposite direction. The thrust is weak. Cometary gravity is weak. So even gentle gas jets can create measurable acceleration over time. We see this constantly in comet tracking. Objects deviate slightly from purely gravitational trajectories because of outgassing thrust. It's expected, it's normal, it's accounted for in standard models. But there are rules, patterns, predictable behaviors. Because outgassing is driven by solar heating, and solar heating varies predictably with distance from the sun and with rotation. As a comet approaches the sun, solar flux increases, temperature rises, outgassing intensifies. As it recedes, the process reverses. Heating decreases, outgassing weakens, thrust diminishes. You get a smooth curve of activity that peaks near perihelion, the closest approach to the sun, and then gradually declines. And because comets rotate, because different regions of the surface cycle through sunlight and shadow, you get modulation. The rotation period becomes visible in the outgassing pattern. Jets turn on when their source region faces the sun, turn off when it rotates into darkness. You see regular variations on the rotation timescale, bright, dim, cycling with the spin. This is textbook cometary behavior. We've observed it on dozens of objects, measured it, modeled it, built our understanding from hundreds of examples, and none of those examples prepared us for what 3I Atlas is doing. First problem, the timing is wrong. The most dramatic thrust events, the biggest deviations from predicted trajectory, happened after December 19th, after closest approach to Earth, after the object had passed perihelion and started moving away from the sun. Activity should have been decreasing at that point, solar heating diminishing, temperature dropping, outgassing weakening, but instead, activity increased. More thrust events, larger deviations, greater unpredictability. That's backwards. That's the opposite of how thermal processes work. Unless there's extreme thermal lag, unless heat absorbed during the approach is taking a long time to penetrate to subsurface ice, but thermal lag should create smooth delayed response, not episodic bursts weeks after peak heating. Second problem, the directional changes are too fast. Comets rotate. Typical periods range from hours to days. Let's say 3I Atlas has a 16-hour rotation period, which is reasonable based on brightness variations we've observed. That means any fixed vent on the surface completes one full rotation every 16 hours. If outgassing is coming from a specific location, the thrust direction should sweep around once per rotation. You'd see a predictable pattern. Thrust pointing one way, then gradually rotating to point another way, then cycling back. Smooth changes on a 16-hour timescale. But the directional changes in 3I Atlas's thrust don't match that pattern, don't correlate with rotation, happen on different timescales, sometimes faster than rotation allows, sometimes with abrupt shifts that can't be explained by a fixed vent rotating with the surface, as if the thrust source is changing location, or changing orientation independent of the body's rotation, or multiple vents are turning on and off in sequence. All of those scenarios require special pleading. require invoking specific conditions that we have no independent evidence for. Maybe there are multiple active regions. Maybe subsurface structure channels gas to different surface locations at different times. Maybe pressure builds and releases unpredictably, creating episodic venting from random locations. Maybe. Stack enough maybes, and you're not explaining anymore. You're inventing stories to preserve the conclusion you want. Third problem. The magnitude is wrong for the size. This is where the physics becomes quantitatively constraining rather than just qualitatively puzzling. Because outgassing thrust depends on how much gas is being released, and gas release depends on surface area and composition and temperature and sublimation rate, all of which we can estimate or measure. 3I Atlas is small. New size estimates, refined from better observations during the close approach, put the nucleus somewhere between 800 and 1,000 meters in diameter. That's modest, a few football fields across. Not tiny by asteroid standards, but definitely on the small end for active comets. Surface area scales with the square of the radius. For an 800-meter diameter sphere, you're looking at roughly 2 million square meters of surface. That sounds like a lot until you realize that most of that surface isn't active, isn't producing gas. Only the sunlit portions sublimate efficiently, and only if they're composed of volatile material rather than non-volatile rock. Let's be generous. Let's say half the surface is active and producing gas at high rates, 1 million square meters. Solar flux at the distance 3I Atlas was during peak activity drive sublimation. We can calculate expected gas production rates based on composition. If it's water ice, you get a certain sublimation rate per square meter at a given temperature. If it's more volatile ices like CO2, you get higher rates. Plug in the numbers, do the calculation, and you get thrust levels that are measurable but modest, enough to create small deviations over time, enough to require accounting for in trajectory models, not enough to create the large, repeated directional changes we're observing, not by an order of magnitude. To produce the observed thrust, 3I Atlas would need to be outgassing at rates that exceed what its surface area can support, would need to be releasing gas so vigorously that the energy budget doesn't work. Solar heating provides only so much energy. Sublimation requires energy to break molecular bonds and convert solid to gas. The energy balance constrains how much gas can be produced, and the constraint says the observed thrust is too strong. Unless the object is much larger than we think, but we've got good size estimates now from multiple independent methods. Light curve analysis showing how brightness varies with rotation, thermal modeling from infrared observations, direct imaging from close approach, all converging on 800 to 1,000 meters, not 10 kilometers, not even 2 kilometers, small. Or unless the composition is dominated by super volatile ices, materials that sublimate so readily that normal energy input creates extraordinary gas production, except spectroscopy shows what's in the coma, shows what molecules are being released, and while CO2 is prominent, while the composition is unusual, it's not dominated by exotic hypervolatiles that would explain the activity level. Or unless there's an internal energy source, something beyond solar heating driving the outgassing, radioactive decay, chemical reactions, tidal heating from... Wait, there's no large body nearby to create tidal forces during most of the trajectory. So where would internal heating come from? And even if it existed, why would it create episodic rather than continuous outgassing? The explanations keep failing, keep requiring additional assumptions that aren't supported by observations. And at some point, you have to ask whether you're trying to force the data into a framework it doesn't fit, or whether the framework itself needs to be questioned. But there's an even deeper problem with the outgassing explanation, one that goes to structural stability. Because if 3I Atlas is small and releasing gas violently enough to create the observed thrust, it should be tearing itself apart. Comets aren't solid monoliths. They're not steel spheres that can withstand enormous internal pressures. They're aggregates. Collections of smaller pieces loosely bound by weak gravity, and maybe some material strength from ice acting as a binder. We call them rubble piles, and rubble piles have very low tensile strength, very limited ability to resist forces trying to pull them apart. When gas builds up subsurface, when pressure increases, when vents open and release that pressure explosively, the forces involved create stress. Thermal stress from differential heating, mechanical stress from pressure gradients, rotational stress if the object is spinning fast. All of these stresses work against the weak forces holding the rubble pile together. For large comets several kilometers across, self-gravity is strong enough to overcome most of these stresses. The mass is large, gravity is significant. The comet holds together even when outgassing vigorously. But for small comets under a kilometer, gravity is weak, very weak. The escape velocity from an 800-meter comet is measured in centimeters per second, walking speed. If you stood on the surface and jumped, you'd achieve orbit. When stresses exceed gravitational binding, the comet fragments, breaks into pieces that drift apart. We've seen this happen. Multiple comets have disintegrated under exactly this kind of stress. Shoemaker-Levy 9 broke into more than 20 fragments before impacting Jupiter. Comet Linear fragmented into dozens of pieces. Comet Schwarzmann-Wachmann 3 shattered. Comet Atlas, different one, completely disintegrated in 2020. The pattern is clear. Small comets with strong outgassing don't last. They crack, they fragment, pieces separate. Sometimes the nucleus survives as a smaller remnant. Sometimes the whole thing disperses into dust, but structural integrity fails. That's what happens when you stress a weak aggregate beyond its binding strength. 3I Atlas should be fragmenting, should be showing signs of structural failure. Brightness variations from pieces separating, spectroscopic signatures of fresh material being exposed as surface layers crack, possibly even direct imaging of multiple components if the separation is large enough. But we're not seeing that. The object appears intact, coherent, holding together despite producing thrust levels that should be ripping it apart. So, how is it surviving? Is it somehow stronger than typical comets? Made of material with higher tensile strength, bound by something other than weak gravity and ice cement? Or is the outgassing not as violent as the trajectory deviations suggest, and the thrust is coming from something else entirely? These questions don't have satisfying answers within the conventional framework. Every explanation requires special conditions, unusual composition, exotic structure, atypical behavior. And when you need multiple special conditions all operating simultaneously to make the natural explanation work, Occam's razor starts cutting in uncomfortable directions. The dust situation adds another layer of strangeness that compounds rather than resolves the puzzle. Because around the nucleus, obscuring it partially, preventing direct observation of the actual solid body, is a cloud of dust. This is normal for comets. Dust gets released along with gas, entrained in the outflow, carried away from the nucleus. It scatters sunlight, creates the visible coma that makes comets easy to spot, all expected. But the dust around 3I Atlas has characteristics that don't match the chaotic release you'd expect from natural fragmentation and sublimation. The particle size distribution is narrow, tightly concentrated around 10 micrometers in diameter, 10 millionths of a meter. Particles in that size range have specific optical properties. They scatter light efficiently, reflect in ways that create high brightness, make the dust cloud more visible than the nucleus it surrounds. Most comets release dust across a broad range of sizes. You get everything from microscopic grains smaller than the wavelength of light to centimeter-scale chunks. The distribution follows power laws, lots of small particles, fewer medium ones, very few large pieces. It's the natural result of random fragmentation. Ice cracks unpredictably, pieces break off in various sizes. Gas carries away whatever it can lift. The result is a mess. a distribution that spans orders of magnitude in particle size. But 3I Atlas's dust is concentrated, narrow, specific, as if there's selection happening, as if particles of a particular size are being preferentially released while other sizes are retained or not produced. That's not random, that's not chaotic ice cracking, that's organized in a way that natural processes struggle to explain. Why 10 micrometers? That size is interesting optically. It's near the wavelength of visible light. Scattering from particles that size is efficient. They create maximum brightness for a given mass of dust. If you were trying to make a dust cloud as visible as possible, if you wanted to maximize reflected sunlight per kilogram of material released, you'd select 10 micrometer particles. They're optimal. Is that coincidence? Is it just happenstance that the narrow size distribution happens to peak at the most visible size? Or is there a reason, some process that favors that particular size, some mechanism we're not aware of that preferentially releases those grains? The narrow size distribution also affects how the dust interacts with radiation pressure. Larger particles, tens or hundreds of micrometers across, have more mass relative to their surface area. They're harder for solar radiation to push. They resist acceleration by light pressure, can maintain trajectories that aren't purely radial outward from the sun. And that's relevant because the anti-tail, that structure pointing sunward when all normal comet tails point away, requires heavy particles, requires grains that can resist radiation pressure enough to move in directions other than directly away from the sun. Particles around 10 micrometers are right at the threshold. Large enough to resist somewhat, small enough to be carried by gas initially, the perfect size for creating anomalous tail structures. Is that also coincidence? That the same narrow size distribution that makes the dust maximally visible also makes it capable of forming the strange anti-tail structure? Or are these connected? Is there one mechanism producing both effects? One process selecting particle size for reasons we don't understand? The dust cloud creates an observational problem beyond just being interesting in its own right, because when you point a telescope at 3I Atlas, when you try to measure its position precisely, you're not seeing the nucleus directly, you're seeing the integrated light from the entire dust cloud, the brightness centroid, the geometric center of the light distribution, and you're assuming that centroid corresponds to where the nucleus actually is, that the dust is distributed symmetrically around the solid body, so that the brightness peak marks the position of the mass concentration. But what if that assumption is wrong? What if the dust is asymmetric, denser on one side because of preferential release, or because radiation pressure has pushed more dust in certain directions? Then the brightness centroid is offset from the true nucleus position. Your position measurement, however precise, is measuring the wrong thing. And if your positions are systematically offset, your velocity calculations are wrong. Your trajectory predictions are based on faulty data, and the apparent deviations might be partially artifacts of measurement rather than genuine course changes. This could explain some of the uncertainty, could account for why the trajectory cone is expanding so dramatically. Measurement error propagating and compounding. But it doesn't explain the episodic nature. Doesn't explain why deviations happen in discrete events. Measurement errors are random, noisy. They don't create patterns, don't synchronize with other phenomena like brightness pulses and X-ray emissions. So yes, the dust obscuration is making precise tracking harder. Yes, there's additional uncertainty from not being able to see the nucleus directly. But something real is happening beneath that uncertainty. Some physical process is creating actual thrust events that are genuinely changing the trajectory, not just appearing to change it because of measurement issues. And the dust itself, with its narrow size distribution and its optical properties and its ability to form anomalous structures, is evidence that whatever process is operating is organized rather than chaotic, is selective rather than random, is producing specific outcomes rather than just releasing whatever happens to break loose. This organization, this structure, this apparent control over what gets released and when, is what makes the natural explanation increasingly difficult to maintain without invoking scenarios so specific and so unlikely that they strain credibility more than alternative explanations would. Let's talk about the anti-tail in more detail because it's central to understanding why the conventional framework is failing. Normal comet tails point away from the sun. This is first-year astronomy. This is the kind of fact that gets repeated in every popular science book about comets. And it's true because the physics is simple and unavoidable. Solar radiation pressure pushes dust outward. Photons from the sun carry momentum. When they strike dust particles and get absorbed or scattered, they transfer that momentum. For small particles, the push is strong relative to the particle's mass. The dust gets accelerated away from the sun. That creates the dust tail, curved and diffuse, following the comet's orbital path but always pointing away from the heat source. The solar wind pushes ionized gas outward even more directly. The stream of charged particles flowing from the sun interacts with the plasma in the comet's coma, carries it away, creates the ion tail, straighter and bluer than the dust tail, pointing directly radial from the sun. Both tails point away, always, without exception in normal comets. But occasionally you see an anti-tail, a structure that appears to point toward the sun. And this is usually explained as a viewing geometry effect, an optical illusion, because comets shed dust continuously as they move along their orbits. That dust spreads out, creating a trail that extends both forward and backward along the orbital path. Most of the time, you're viewing that trail from an angle where you see it extending behind the comet. But if Earth happens to be positioned just right, if you're looking nearly edge-on at the dust trail, you can see it extending in both directions. The portion that looks like it's pointing sunward is the anti-tail, but it's not actually moving toward the sun. It's just older dust from past positions, visible because of your viewing angle. This is documented, well understood. We've seen it on multiple comets. Nothing mysterious. Pure geometry. The dust particles are still being pushed outward by radiation pressure. The anti-tail appearance is just because you're looking through the dust distribution rather than at it from the side. But with 3I Atlas, the anti-tail structure doesn't quite match what you'd expect from pure viewing geometry. It's too prominent, too well defined. For a projection effect to create such a distinct structure, the dust distribution would need to be very specific, very organized, very symmetrical along the orbital path. And here's the critical detail. If the anti-tail is real, if there's actually dust on the sunward side of the nucleus rather than just the appearance of it from viewing angle, then that dust has to be heavy, has to consist of particles large enough that radiation pressure can't immediately blow them away. Light dust, particles a few micrometers or smaller, gets pushed outward fast, can't linger on the sunward side, can't accumulate there. But heavy particles, grains tens of micrometers or larger, can resist radiation pressure, can maintain trajectories that aren't purely radial, can create structures that don't conform to the simple model of everything being pushed directly away from the sun. So if the anti-tail is genuine rather than illusory, it tells us the dust includes heavy components. And combined with the narrow size distribution around 10 micrometers we discussed earlier, it suggests there's a range of particle sizes being released. Maybe 10 micrometers dominates the visible coma, creating the brightness we observe, while larger grains create the anti-tail structure. But that creates questions about the release mechanism, because different size particles get released through different processes. Small grains get carried by gas flow, entrained in the sublimation-driven wind. Larger particles need more energy to lift off, need stronger gas jets or explosive events or some process beyond gentle sublimation. And if both are happening, if the comet is releasing 10 micrometer grains continuously while occasionally ejecting larger particles that create the anti-tail, then there are multiple processes operating. Multiple mechanisms, not just simple thermal sublimation, but a suite of activities that engage at different times and produce different outcomes. This multiplicity is hard to explain naturally, hard to account for through single physical process. You need complexity. internal structure creating different release modes, composition variations across the surface, subsurface pressure systems that operate episodically, thermal gradients that trigger different sublimation regimes. Each additional mechanism you invoke makes the explanation more contrived, more dependent on specific conditions that can't be independently verified. More like a just-so story constructed to fit observations rather than a theory that predicts them. And at some point, as the number of required special conditions grows, the natural explanation becomes less parsimonious than alternatives that might initially seem more exotic but that actually require fewer assumptions. This is the edge where the debate becomes uncomfortable, where researchers start having to choose between stacking unlikely natural scenarios or entertaining possibilities that challenge fundamental assumptions about what kinds of objects exist in the galaxy, where the episodic thrust and the narrow dust distribution and the anti-tail structure and the structural stability all combine into a pattern that looks more like control than like chaos. I want to be absolutely clear about something before we go further. I am not claiming 3I Atlas is artificial, not stating it's a probe or a spacecraft or technology from another civilization. The evidence doesn't support certainty in either direction. But what the evidence does support, what the observations force us to acknowledge, is that the behavior is organized, structured, patterned in ways that natural chaos doesn't normally produce. Whether that organization comes from exotic but natural internal structure, from processes we haven't encountered before because this object formed around a different star under different conditions, or whether it comes from design, from systems built for purposes we don't understand, remains an open question. But the question is legitimate. The data justifies asking it, and dismissing it without examination is no more scientific than accepting it without evidence. The episodic thrust is the clearest example of this organization, because truly random processes, truly chaotic natural systems, don't produce regular patterns, don't create rhythmic behavior, don't show coordination between different phenomena. But 3I Atlas shows exactly that coordination. The brightness pulses that have been documented for months show regular periodicity. The X-ray emissions pulse in synchronization. The ultraviolet flickering matches the pattern. And now the trajectory deviations, the thrust events themselves, are episodic on similar timescales. That's not 4 separate random processes happening to align by chance. That's one underlying mechanism manifesting in multiple ways. One system creating brightness changes and X-ray emission and UV flickering and thrust all together because they're all aspects of whatever is actually operating. And that raises the question, what natural mechanism produces this kind of multi-phenomenal coordination? What single process creates organized pulses across electromagnetic spectrum and mechanical thrust simultaneously? Answers exist. You can construct scenarios, rotating active regions that periodically face the sun and become briefly active, subsurface reservoirs that build pressure and release rhythmically, resonant phenomena in the comet's interior creating feedback loops that produce regular cycles. Each is possible. Each has been invoked to explain behavior in other comets or asteroids or icy moons, but none fits perfectly. Rotation doesn't match the pulse timing. Pressure cycles require very specific structures we can't verify. Resonances should be stable, but the pulses show variation and jitter. Every natural explanation requires adding parameters and conditions that make the model more complex rather than simpler. And simplicity, parsimony, Occam's razor, these aren't just philosophical preferences. They're methodological tools that help distinguish between explanations that actually explain and explanations that just accommodate, between theories that predict and models that merely fit after the fact. When the natural explanation requires 10 assumptions and the artificial explanation requires 3, which is actually simpler? The question isn't rhetorical. It's central to how we evaluate competing hypotheses when data is ambiguous. The trajectory uncertainty, the expanding cone of possible positions that makes long-term prediction impossible, is the practical consequence of the episodic thrust. Because if we could predict when the next thrust event would occur and how strong it would be and what direction it would push, we could incorporate that into trajectory models and regain predictability, could build equations that account for the thrust and still tell you where the object will be months from now. But we can't predict the thrust events, can't model them, can't even find correlations with measurable parameters that would let us build empirical relationships. They happen when they happen, with magnitudes that vary, in directions that change, and each one adds uncertainty that compounds over time. This is unprecedented in the history of tracked objects. We've had spacecraft fail and become uncontrollable. We've had asteroids whose trajectories were hard to predict because we didn't have enough observations. But we've never had an object we're actively tracking that we have continuous data on become fundamentally unpredictable because its behavior is episodic and variable. And the implications are profound. Because if you ask an astronomer today where 3I Atlas will be in 6 months, they cannot tell you, not with any precision, not even to within millions of kilometers. The cone of uncertainty has expanded to the point where the answer is effectively somewhere in this vast region of space, rather than at these specific coordinates. That's a failure of prediction. A breakdown in our ability to apply physics to forecast future states. And that breakdown comes not from ignorance of the laws that govern motion, but from the object's refusal to follow those laws in predictable ways, from behavior that looks more like agency than like determinism. Whether that appearance is real or illusory, whether we're seeing actual agency or just natural processes we don't understand yet, the fact remains, prediction has failed. And failure demands explanation. The CO2 hypothesis seemed like salvation when it first emerged. Finally, an explanation grounded in established cometary physics that could account for at least some of the unusual behavior. Carbon dioxide ice is more volatile than water ice, sublimates at lower temperatures. Can create activity farther from the sun where water-based comets would remain dormant. And spectroscopic observations confirmed it. CO2 was prominent in the coma, dominating the early outgassing signature, showing up strongly in infrared measurements. This explained why 3I Atlas was active so early in its approach, why it was producing a visible coma and releasing gas when it was still far enough from the sun that water ice should have been frozen solid. CO2 doesn't need intense heating, can sublimate in the cold outer solar system, can create jets and thrust and all the features we associate with active comets without requiring the object to be close to perihelion. The early observations fit perfectly. The bright coma detected months before closest approach. The strong outgassing visible even when the object was beyond Mars orbit. The spectroscopic signatures showing carbon dioxide as a major component. All consistent with a CO2-dominated comet behaving exactly as CO2-dominated comets should behave. But then December 19th happened, and the behavior after closest approach broke the CO2 explanation as thoroughly as the episodic thrust breaks simple gravitational models. Because CO2-driven activity, like all thermally driven sublimation, follows temperature, and temperature follows solar distance. As you move closer to the sun, heating increases, temperature rises, sublimation intensifies. As you move away, the process reverses. Cooling, decreased sublimation, weakening activity. The curve is smooth, predictable. Peaks at perihelion or shortly after if there's thermal lag allowing absorbed heat to continue driving sublimation even as external heating decreases. But within days or weeks, activity should decline. Should follow a gentle downslope matching the decreasing solar flux as distance increases. 3I Atlas did the opposite. Activity increased after December 19th. More episodic thrust events, larger trajectory deviations, greater intensity in the pulses across all wavelengths. The object got more active as it moved away from the sun, as heating decreased, as the energy source that should drive CO2 sublimation weakened. That's thermodynamically backwards. You can't get increasing activity from decreasing energy input unless there's storage. Unless heat absorbed during approach is being retained somehow, working its way through the interior, reaching subsurface ice deposits that then sublimate delayed from the peak heating. Thermal lag is real. We see it in comets. But it creates smooth delayed response, not increasing episodic activity weeks after the fact. And it doesn't explain the directionality changes. CO2 sublimation creates thrust in the direction gas escapes. If vents are fixed to surface locations, the thrust direction rotates with the comet's spin. You get modulation on the rotation period. Predictable changes as active regions face different directions. That's normal behavior we can model. But 3I Atlas's thrust direction changes aren't matching rotation, aren't cycling smoothly, are shifting on timescales that don't correlate with the measured spin period, as if the vents themselves are moving, or as if multiple vents scattered across the surface are activating and deactivating independently, creating thrust vectors that sum unpredictably as different combinations engage. The CO2 hypothesis doesn't account for this, doesn't provide a mechanism for vents to turn on and off episodically, for thrust direction to change independent of rotation, for activity to increase when it should decrease. The model worked beautifully for the early observations, explained the distant activity perfectly, and then became inadequate the moment the object started behaving strangely after closest approach. So researchers are left with a partial explanation. CO2 accounts for the first act, gets us through the approach phase, but fails completely for the second act, the current behavior that's making prediction impossible. And partial explanations are frustrating because they dangle the promise of understanding while leaving the most interesting questions unanswered. The energy budget problem compounds rather than resolves with the CO2 hypothesis. Because yes, CO2 is more volatile than water, requires less energy to sublimate, but that actually makes the energy problem worse rather than better. If sublimation requires less energy per molecule, then the same energy input should produce even more activity than water ice would, should create even stronger outgassing for a given solar flux. But we're already seeing activity levels that exceed what the solar flux at 3I Atlas's distance should be able to drive. Adding CO2, which sublimates more easily, doesn't close that gap. It widens it, makes the discrepancy larger because now we're saying the material is even more responsive to heating than water ice. Yet the heating available isn't sufficient to explain the observed activity, unless there's internal heating, unless energy is coming from somewhere besides the sun, radioactive decay in the interior, chemical reactions, something generating heat that supplements solar input and drives sublimation beyond what external heating alone could achieve. But radioactive heating requires specific isotopes in specific concentrations. We'd need the interior to be enriched in elements like aluminum-26 or iron-60, short-lived radioactive species that can generate substantial heat. These isotopes exist, are incorporated into forming planetary bodies, decay over millions of years, releasing energy, but in an object 800 meters across, in something that small, radioactive heating should be negligible. Not enough mass, not enough radioactive material. The heat generation would be tiny, far too small to drive the activity we're seeing. Chemical reactions are possible in principle. Certain compounds can react exothermically, releasing heat when they interact. But you need specific chemistry, need reactants to be present in the right proportions, need conditions that allow reaction to proceed, and you need the reactions to be episodic somehow, turning on and off, creating bursts of heat that drive bursts of sublimation. That's a lot of very specific requirements, and we don't have evidence for the chemistry that would make it work. Spectroscopy shows what's in the coma, but doesn't reveal what might be reacting in the interior. We're inferring reactions because we need heat sources, not because we've detected the reactants or products. This is the problem with the energy budget. Every explanation requires invoking processes we can't verify, internal heating we can't measure, exotic chemistry we can't detect, subsurface structures we can't observe. We're building models where the interesting parts are hidden, where the mechanisms that would make everything work are tucked inside the object beyond observational reach. And that's convenient. too convenient, because unfalsifiable explanations that invoke hidden mechanisms that can't be tested, aren't really explanations at all. They're speculations dressed up as physics, might be correct, might be completely wrong, but without ways to test them, to verify or falsify the claims, they're just stories. The structural stability paradox is where the trilemma becomes impossible to ignore, because you can't have all three simultaneously under normal physics, can't be small and active and stable together. Pick any two and you can construct a scenario that works. But all three? The equations don't balance. If it's small, 800 to 1000 meters in diameter, then its self-gravity is weak. Escape velocity is measured in centimeters per second. Material strength from ice cementation might provide some cohesion, but not much. The tensile strength of ice is low. It cracks easily, fractures under stress. An 800-meter rubble pile held together by weak gravity and brittle ice shouldn't be able to withstand strong outgassing if it's active, producing thrust strong enough to measurably change its trajectory, strong enough to create deviations that compound over weeks. Then the gas release is vigorous. Pressure is building subsurface and escaping forcefully. That creates stress. Mechanical forces trying to crack the structure, thermal gradients causing expansion and contraction, rotational forces if the object is spinning, all working against structural integrity. If it's stable, holding together without fragmenting despite the stresses, then either it's much larger than we think, giving it stronger gravity and more cohesion, or it's made of something much stronger than normal cometary material, or the activity isn't actually as violent as the trajectory changes suggest. But we can't adjust size. Multiple independent measurements constrain it to roughly 1 kilometer. We can't invoke exotic super-strong materials without spectroscopic evidence, and we can't deny the trajectory deviations because they're measured directly and confirmed by multiple observatories, so we're stuck. The trilemma locks: small size, high activity, structural stability. Choose any two, except that the third contradicts observations or find a way out of the framework entirely. And there are ways out. They just require questioning assumptions that feel fundamental. What if the object isn't a rubble pile? What if it's coherent, solid or nearly solid rather than a loose aggregate? Then material strength could be much higher, could resist stresses that would tear apart loose collection of chunks, could maintain integrity despite vigorous outgassing. But solid comets are uncommon. Most are rubble piles. We know this from observations of cometary breakups, from how they respond to tidal forces, from their low densities. Solid icy bodies exist. Moons of the outer planets are examples, but those formed under different conditions. In strong gravitational fields, with processes that compacted and solidified material. Comets form in the outer regions of protoplanetary disks, form from aggregation of smaller pieces, should be porous, should be weak. An interstellar comet might be different, might have formed under conditions we don't see in our solar system, around a different star with a different temperature profile, with different chemistry, with processes that created coherent structures rather than rubble piles. Possible, speculative, but possible. And that's convenient, too convenient, because unfalsifiable explanations that invoke hidden mechanisms that can't be tested, aren't really explanations at all. They're speculations dressed up as physics. Might be correct, might be completely wrong, but without ways to test them, to verify or falsify the claims, they're just stories. The structural stability paradox is where the trilemma becomes impossible to ignore, because you can't have all three simultaneously under normal physics, can't be small and active and stable together. Pick any two and you can construct a scenario that works, but all three, the equations don't balance. Or what if there's internal structure, framework, support, something holding the object together that isn't just gravity and ice strength? Metal framework would do it. could provide tensile strength far exceeding what ice has, could maintain shape under stresses that would disintegrate natural aggregates. But metal framework implies construction, implies design, takes us into territory that requires explaining not just what holds it together, but who built it and why. This is the uncomfortable space the analysis occupies. Every natural explanation for the stability requires special circumstances, unusual formation conditions, exotic composition, atypical structure. And when you're already invoking special circumstances for the activity level and for the episodic behavior and for the dust distribution, when the entire model is built on stacked special cases, the cumulative probability starts to strain. Not impossible. Still possible that every special circumstance is real, that 3I Atlas genuinely is the result of natural processes that just happen to be very unusual in multiple independent ways, but improbable, increasingly improbable as each new special circumstance gets added to make the model fit observations. And that's when alternative explanations start to look less exotic than the natural ones. When design, when deliberate construction, when artificial origin becomes a simpler hypothesis than natural formation with 10 different unusual features, all coincidentally aligned. The dust grain size specificity might be the most overlooked piece of evidence because it's technical and requires understanding optics and scattering theory to appreciate why it matters. But it's profound, because in natural fragmentation, in chaotic processes where ice breaks and sublimates and releases embedded particles, you don't get narrow size distributions. You get spreads, you get power laws, you get everything from nanoscale grains to centimeter chunks all mixed together. The size distribution follows from the physics of breaking. When solid material fractures, cracks propagate randomly. Some pieces are small, some are medium, some are large. The distribution of sizes follows mathematical relationships that have been studied extensively. We know what natural fragmentation looks like. We've observed it in countless contexts, from laboratory experiments to asteroid collisions to cometary outbursts. And natural distributions are broad, log normal or power law, spanning orders of magnitude. You might have a peak, a most common size, but with wide wings extending to much smaller and much larger particles. That's the signature of randomness, of chaos, of processes that don't select but just break whatever happens to break. 3I Atlas's dust distribution is narrow, concentrated around 10 micrometers with much less spread than natural processes produce, as if something is selecting that size, preferentially releasing those grains while retaining or not producing others. And 10 micrometers is optically significant, is near the wavelength of visible light, scatters efficiently, creates maximum brightness per unit mass. If you wanted to make a cloud as visible as possible, if you were trying to maximize how much sunlight gets reflected back toward observers, you'd choose 10 micrometer particles. They're optimal. Smaller grains don't scatter as well per particle. Larger ones have more mass per scattering cross-section, are less efficient. 10 micrometers is the sweet spot. Is that coincidence? That the narrow distribution happens to peak at the most visible size? Or is there causation? Is visibility the reason for the size selection? And if visibility is intentional, if there's purpose behind creating a bright dust cloud, then we're no longer talking about natural processes. We're talking about function, about design serving a goal, about systems operating to achieve outcomes. The same size is also relevant for the anti-tail, for creating structures that can resist radiation pressure enough to appear on the sunward side. 10 micrometers is large enough to not be immediately blown away, small enough to be lifted by gas initially, right at the threshold where behavior becomes interesting, where particles can move in directions that aren't purely radial away from the sun. Again, is this coincidence? That the same size serves multiple purposes, or are the purposes connected? Is there one reason for the size selection that achieves multiple functional goals simultaneously? Natural explanations exist. You can construct scenarios where specific sublimation conditions favor certain grain sizes, where particles below or above that size either don't get released or get released differently, where the 10 micrometer peak emerges from the details of how ice fractures and gas entrains particles. But those scenarios require fine-tuning, require precise conditions that we can't verify, require assuming the physics works in ways we haven't observed in other comets. While the functional explanation is simple, if the dust serves purposes, if visibility and anti-tail formation are goals, then selecting the optimal size makes sense, is straightforward, doesn't require fine-tuning beyond choose the size that works best. Occam's razor doesn't always favor the explanation that feels most conventional. Sometimes it favors the explanation that actually requires fewer assumptions. And when the natural explanation needs 6 different special conditions while the designed explanation needs only built for purpose, the simplicity calculation can surprise you. The timing correlation with other phenomena is where the pattern becomes impossible to dismiss as coincidence. Because if the episodic thrust were the only unusual feature, if everything else about 3I Atlas were normal and only the trajectory showed these deviations, you could focus entirely on finding natural mechanisms for the thrust. Could isolate that one problem and work on solving it without worrying about broader implications. But the episodic thrust is synchronized with other pulsing phenomena. The brightness varies episodically. Not smoothly with rotation, but with pulses, regular timing, heartbeat pattern that's been documented for months. The X-ray emissions pulse, regular bursts at specific frequencies, rhythmic pattern that doesn't match continuous processes. The ultraviolet flickering pulses, same timing, same rhythm, all coordinated. And now the thrust pulses with the same characteristics, episodic, rhythmic, coordinated with the electromagnetic signatures. 4 independent phenomena, all showing the same pattern, all pulsing together or in phase relationships that suggest common origin. That's not 4 separate random processes. That's one mechanism creating multiple observable effects. One system whose operation produces brightness, changes, and X-rays and UV emissions and thrust simultaneously, because they're all aspects of whatever is actually running. Natural systems can create multiple effects from single causes. A volcanic eruption produces seismic waves and gas emissions and thermal signatures all together because they all result from magma moving and escaping. A pulsar creates radio pulses and X-ray pulses, and sometimes gamma-ray pulses, all synchronized because they all come from the rotating magnetic field of the neutron star. So synchronized multi-phenomenal signatures aren't inherently unnatural, but they require identifying the mechanism, requires explaining what single process creates all the correlated effects. And for 3I Atlas, that explanation is missing. No proposed mechanism accounts for brightness pulses and X-ray bursts and UV flickers and trajectory changes all together in the rhythmic pattern we're observing. Rotating active regions don't work. Rotation period doesn't match pulse timing. Subsurface pressure cycles don't work. Can't explain electromagnetic emissions. Thermal processes don't work. Don't create X-rays. Magnetic phenomena don't work. Comets don't have strong fields. Every natural mechanism explains part of the pattern. None explains all of it. And when you try to combine mechanisms, when you invoke multiple processes all happening to operate in synchronization, you're not explaining anymore. You're describing, cataloging what you see without identifying why it happens. The alternative is that the pattern comes from design, from systems operating according to programmed sequences, from processes that cycle because they're controlled rather than because natural resonances create rhythm, from mechanism that produces multiple outputs simultaneously because that's how it was built to function. That's speculation. But it's speculation that accounts for the observations more completely than the alternatives do. Doesn't require assuming multiple independent processes somehow synchronize through mechanisms we can't identify. just requires one system operating with multiple manifestations. And when one speculative explanation accounts for more observations with fewer assumptions than multiple conventional explanations combined, the probability calculations shift. The posterior odds change. What felt like exotic hypothesis starts looking more probable than what felt like safe conventional science. The retroactive origin uncertainty is a consequence that deserves more attention than it's getting, because when researchers originally calculated where 3I Atlas came from, when they backtracked the trajectory to determine which direction in the galaxy it arrived from, they assumed the path was clean, was purely gravitational, followed deterministic equations that could be run backward as easily as forward. And that analysis pointed to Sagittarius, specific region of sky, same region where the WOW signal originated decades ago, same region where the gamma-ray burst GRB 25072b came from in July 2025. Provocative coincidence, pattern that suggested possible connection between the burst and the object's detection and maybe even the signal from 1977. But that calculation assumed no course changes during approach, assumed the object was passively falling through the solar system under gravity alone. If there were thrust events before we started tracking in July 2025, if the object was maneuvering during the approach phase before we detected it, then every course change shifts the origin point, changes the backtracking calculation, makes the conclusion about where it came from uncertain. We've only been tracking for 6 months, have data from July to now. Before July, the object was too faint, too far, not detected. What it was doing during that period is unknown. If episodic thrust started months or years before detection, if course changes were happening throughout the approach, then the origin calculation is wrong, not slightly wrong, potentially completely wrong. The object could have come from a different region of the galaxy entirely. The Sagittarius connection could be artifact of assuming straight-line travel. The coincidences with the gamma-ray burst and WOW signal could be meaningless. We don't know. Can't know without tracking data from the full approach trajectory. And that data doesn't exist, can't be recovered. The past is opaque. This undermines confidence in origin claims, makes statements about where the object came from provisional rather than definitive, and it highlights how much interpretation depends on assumptions we can't verify. We assume certain things about how objects behave, build analysis on those assumptions, draw conclusions that seem solid until the assumptions turn out wrong. And when assumptions fail, when the foundation proves shakier than we thought, all the conclusions built on that foundation become suspect, not necessarily wrong, but uncertain, requiring re-evaluation. The same logic applies to predictions. If we can't model the past because we don't know what thrust events occurred before detection, we can't model the future because we don't know what thrust events will occur before they happen. The trajectory is fundamentally uncertain in both directions. Backtracking and forward projection both fail. We're left with only the present, with real-time tracking showing where the object is now and documenting what it does as it does it. That's a profound limitation. Reduces astronomy from predictive science to observational description. We can watch, can catalogue, can document, but can't forecast. Can't calculate where the object will be next week or next month with any confidence. Can only wait and see, tracking continuously, responding to deviations as they occur. And that reduction, that loss of predictive power, is itself evidence that something unusual is happening. Because normal objects follow equations that work in both time directions, that let you reconstruct the past and predict the future with equal facility. When that breaks down, when an object becomes unpredictable, you're seeing behavior that violates the assumptions underlying standard mechanics. Violations can come from ignorance, from not knowing all the forces involved, from missing some relevant physics, but they can also come from agency, from systems that respond and adapt rather than just following deterministic laws, from control rather than passivity. Distinguishing between those possibilities based on limited observations is difficult. may be impossible without additional data that we don't currently have and might never get. But the question is legitimate. The uncertainty is real. And dismissing the possibility of agency without examining why prediction is failing is intellectually lazy. The Jupiter encounter was supposed to be the test, was supposed to be the moment when ambiguity resolved, when we'd see whether the object maneuvered during the gravity assist, whether it showed behaviors that couldn't be explained through natural processes, whether the pattern of course changes continued or stopped or intensified. March 2026, just weeks away now. The trajectory, despite all the uncertainty, still points toward a close approach to Jupiter. 52 million kilometers, close enough for substantial gravitational interaction, close enough to use the planet as a slingshot, stealing momentum and gaining velocity for the exit from the solar system. And the geometry is nearly optimal. The approach angle and velocity are almost perfectly aligned to maximize the gravity assist effect, to extract maximum energy from Jupiter's orbital motion and add it to the object's velocity. If you were planning a trajectory, if you were designing a route through the solar system that visits Earth and then uses Jupiter for departure boost, you'd choose almost exactly the path 3I Atlas is following. Is that coincidence? Is it just happenstance that the trajectory happens to be ideal for a two-planet visit with optimized gravity assist? Or is there intention? Is the geometry evidence of planning rather than chance? The coincidence isn't impossible, isn't even particularly improbable if you consider all the interstellar objects that pass through and only notice the ones with interesting geometries. Selection bias could explain it. We're paying attention to this object because its trajectory was unusual. The fact that it's unusual isn't therefore evidence of design because we wouldn't be looking carefully at objects with boring trajectories. But combined with everything else, the episodic thrust, the dust specificity, the multi-phenomenal synchronization, the structural stability, each coincidence individually is explicable. Together they create a pattern that's harder to dismiss. And Jupiter was supposed to be where the pattern either continued or broke, where we'd see the next maneuver and confirm that yes, this is deliberate navigation following a plan, or where we'd see natural behavior and confirm that no, the previous course changes were just outgassing that happened to look organized. Except we're not waiting for Jupiter anymore. The test is already happening, has been happening since December 19th. The episodic thrust events are occurring now. Multiple deviations documented. Pattern continuing post-perihelion. The behavior we were waiting to see at Jupiter is visible right now, before the encounter, removing the ambiguity about whether maneuvers would happen or not. They are happening. They're documented. They're real. The question isn't whether the object will maneuver at Jupiter. The question is what it will do when it gets there, given that it's already maneuvering regularly. Will the activity intensify? Will there be a specific course correction during closest approach? Will the behavior change in Jupiter's magnetosphere and radiation environment? We don't know, can't predict, can only watch and document as it occurs. The test has become continuous observation rather than waiting for a specific moment. And that means answers will come gradually through accumulation of data, through pattern recognition, through slow building of understanding rather than through single definitive observation that resolves all ambiguity. Science often works this way, not through eureka moments but through gradual clarification, through observations accumulating until the picture becomes clear, through hypotheses being tested repeatedly until one emerges as clearly better supported than alternatives. But there's impatience too, because the object is leaving, will pass Jupiter and then head outward beyond Saturn, beyond Uranus, eventually beyond the reach of our telescopes. The window for observation is limited, measured in months or at most a couple of years before it fades to invisibility. And if we haven't figured out what it is by then, if we haven't determined whether it's exotic natural object or something else entirely, we might never know. The data will end, the observations will stop, and we'll be left with incomplete understanding of the third interstellar visitor to pass through our solar system. That incompleteness is frustrating, but it's also realistic. Science doesn't always provide closure, doesn't always answer every question before the opportunity to gather more data expires. Sometimes you're left with partial knowledge, with observations that constrain possibilities without fully determining which possibility is correct, with probability estimates rather than certainties. And maybe that's where we'll end up with 3I Atlas, with estimates, with probably natural but with unusual characteristics, or possibly artificial with X% confidence based on accumulated evidence, not with definitive answer but with constrained uncertainty, with better understanding than we started with, even if we don't achieve complete understanding. The scientific consensus position remains that the object is natural. That's the official stance, that's what review papers will say, that's the default assumption maintained until evidence forces revision. And the evidence, while unusual, while difficult to explain through conventional mechanisms, hasn't yet crossed the threshold that forces that revision for most of the community. But consensus isn't unanimity. There are researchers, credentialed experts with relevant expertise, who assign significant probability to artificial origin, who think the accumulated anomalies are more easily explained through design than through stacked special natural circumstances, who believe the episodic thrust and synchronized pulses and dust specificity all point towards systems rather than chaos. Those researchers are minority, are outside mainstream consensus, but they're not fringe cranks. They're publishing in peer-reviewed journals, they're presenting at conferences, they're making quantitative arguments based on data analysis, and they're not claiming certainty. They're claiming that probability is high enough to warrant serious consideration rather than dismissal, and that's reasonable. That's how science should handle uncertain situations where evidence doesn't clearly favor one interpretation. Maintain openness, acknowledge uncertainty, assign probabilities based on available data, update those probabilities as new data arrives, and resist the temptation to either embrace unconventional explanations prematurely or dismiss them reflexively. The current situation with 3I Atlas is that the natural explanation is struggling, is requiring more and more special assumptions to fit observations, is becoming less parsimonious as each new anomaly emerges. And while that doesn't prove the natural explanation is wrong, it does shift probabilities, does make alternatives that initially seemed unlikely become more competitive. How much the probabilities have shifted is subjective. Different researchers will assess the evidence differently, will assign different weights to the various anomalies, will reach different conclusions about what the data most strongly supports, and that diversity of opinion is healthy. Is how science handles ambiguity, through debate and continued observation and eventual convergence as evidence accumulates. But what's not healthy is dismissing the debate as settled when it clearly isn't, declaring that the object is definitely natural when the data doesn't support that certainty, shutting down inquiry into alternative explanations before those alternatives have been thoroughly examined. That's not scientific caution, that's dogmatism, and it serves neither truth nor understanding. The episodic thrust continues as we speak. The object is out there right now, moving through space, executing thrust events on a schedule we can't predict, following a trajectory we can't calculate, doing something that breaks our models and demands explanation. And in a few weeks, it reaches Jupiter, where the behavior might change, might intensify, might provide the observations that finally tip the probability calculations decisively one way or another, or might just deepen the mystery, might add more anomalies to the list, might force even more special assumptions into the natural framework, might make the artificial hypothesis even more competitive, even though direct evidence of design remains absent. We're living through this in real time. Watching an interstellar visitor behave in ways that challenge our understanding, debating what it means, trying to build models that work, failing repeatedly, revising, trying again. That's science at the frontier. That's what discovery looks like when you're encountering something genuinely new, and whether 3i Atlas turns out to be a comet with exotic but natural properties, or whether it's something else. Something that requires revising our assumptions about what kinds of objects exist in the galaxy. We're learning. We're expanding our understanding. We're being forced to think harder about possibilities we previously dismissed. That's valuable regardless of which explanation ultimately proves correct. That's the scientific process working as it should. Observations challenging theories, theories being revised or replaced, knowledge advancing through the uncomfortable process of confronting data that doesn't fit comfortable categories. The journey continues. The observations accumulate. And the answer, whatever it turns out to be, approaches with each passing day as 3i Atlas speeds toward Jupiter and toward whatever revelations that encounter might bring. The measurement problem runs deeper than most people realize, because when you're trying to track something moving at tens of kilometers per second across hundreds of millions of kilometers of space, when you're measuring positions to accuracy levels measured in fractions of arc seconds, when you're calculating velocities from changes in position over time, every assumption you make about what you're actually observing matters profoundly. And with 3i Atlas, one of those assumptions is breaking down in ways that propagate through every subsequent calculation. The assumption is simple, that the brightness centroid, the geometric center of the light distribution you're measuring, corresponds to the actual position of the nucleus. That where the object appears brightest is where the solid body actually is. For most astronomical observations, this is safe. The thing emitting or reflecting light is the thing you're trying to locate. Brightness peak equals position. Simple. But 3i Atlas is surrounded by dust, that 10 micrometer grain cloud we discussed, thick enough to scatter substantial amounts of sunlight, dense enough to create a brightness distribution that extends well beyond the nucleus itself. And if that dust cloud is asymmetric, if it's denser on one side than the other, then the brightness centroid is offset from the actual nucleus position. It's like trying to find the exact center of a spotlight when all you can see is the glow. If the beam is perfectly symmetric, the brightest point marks the center. But if the beam is tilted or partially blocked or enhanced by atmospheric scattering on one side, the brightness peak shifts. It no longer corresponds to the geometric center of the source. For 3i Atlas, if the dust distribution is asymmetric, and we have reasons to think it might be given the anti-tail structure and the preferential particle sizes, then every position measurement is systematically offset by some unknown amount in some unknown direction. You're measuring where the dust cloud appears brightest, not where the nucleus actually is. And that offset propagates. Position errors become velocity errors when you calculate speed from position changes over time. Velocity errors become trajectory errors when you predict future positions. Trajectory errors become the expanding uncertainty cone that makes long-term prediction impossible. The whole house of cards collapses from the foundation up if the initial assumption about what you're measuring is wrong. Could this explain some of the apparent trajectory deviations? Could the episodic nature be partly artifact of dust cloud asymmetry changing over time as the object rotates and as gas production varies? Possibly. It would create measurement noise that looks like course changes even if the underlying trajectory is smooth. But it can't explain all of it. Can't explain why the apparent deviations correlate with other phenomena. Can't explain the synchronization between position offsets and brightness pulses and X-ray emissions. Measurement artifacts are random, noisy. They don't create patterns, don't correlate with electromagnetic signatures. So yes, the dust obscuration adds uncertainty, makes precise tracking harder, might account for some fraction of the observed deviations. But something real is happening beneath the measurement noise. Some actual physical process is creating thrust that genuinely changes the trajectory, not just appearing to change it because we're measuring the wrong thing. Distinguishing between measurement artifacts and genuine effects requires careful analysis, requires cross-checking observations from multiple instruments with different methodologies, requires looking for correlations that wouldn't exist if the deviations were purely observational errors. And that analysis is ongoing. multiple groups working independently, using different data sets, applying different techniques, and they're converging, not on every detail, but on the basic conclusion that yes, real non-gravitational acceleration is occurring, that the trajectory deviations aren't just measurement noise, that something is producing thrust. Agreement doesn't prove the interpretation is correct, but it does constrain possibilities. Reduces the viable explanations to those that account for actual physical thrust rather than just observational artifacts. The dust itself remains mysterious beyond just being an obstacle to measurement because it's not just present, it's organized, the narrow size distribution, the optical properties, the apparent ability to form structures like the anti-tail that require specific particle characteristics. All of this suggests the dust isn't random debris shed chaotically as ice cracks and sublimates. Natural processes creating organized output usually require specific structures creating that organization. A nozzle creates organized flow from chaotic pressure. A magnetic field organizes plasma into coherent structures. Crystallization creates organized atomic arrangements from liquid disorder. Organization implies mechanism, implies structure that constrains randomness and produces pattern. For 3I Atlas's dust, what mechanism creates the narrow size distribution? What structure preferentially releases 10 micrometer grains while retaining or not producing other sizes? Natural explanations exist. You can construct scenarios involving specific sublimation conditions or specific fracture mechanics or specific gas flow dynamics that favor certain particle sizes. But those scenarios are speculative, built from theory rather than observation because we can't see inside the object, can't verify that the conditions we're assuming actually exist, can't test whether the mechanisms we're proposing actually operate. We're inferring structure from outcome, which is backwards from how science ideally works, where you observe structure and predict outcomes that you then verify. And when you're forced to infer rather than observe, when you're building models from consequences rather than from causes, the models become less constrained, more flexible, capable of accommodating almost any observation by adjusting hidden parameters. That flexibility is both strength and weakness. Strength because you can make the model fit almost anything. Weakness because fitting everything means predicting nothing. A good scientific theory doesn't just accommodate observations, it constrains them, makes predictions that could be wrong, creates expectations that observations might violate, theories that can't be wrong, that adjust to match whatever you find, aren't really theories. They're descriptions, and descriptions don't advance understanding the way genuine explanations do. The natural explanation for 3I Atlas is becoming dangerously descriptive, is accumulating adjustable parameters faster than it's making testable predictions, is fitting observations after the fact rather than predicting them beforehand. And that transition from predictive theory to descriptive accommodation is a warning sign that the framework might be inadequate, not proof that it's wrong, just indication that it's struggling, that the observations are pushing against the limits of what the framework can accommodate, that maybe we need different framework, different basic assumptions to make sense of what we're seeing. The gamma-ray burst connection deserves revisiting because the timing is too precise to ignore, even though the physics connecting a burst 5 billion light-years away to an object in our solar system is completely unclear. GRB 25072b, July 2nd, 2025. Second strongest gamma-ray burst ever recorded. 3 pulses with mathematical timing. First and second pulse separated by 2025 seconds. First and third pulse separated by exactly 4 times that interval. 11/300 seconds. Precise 4.1 ratio. Same day, 3I Atlas detected for the first time. Announced as third confirmed interstellar visitor, shows immediate unusual activity, strong outgassing, organized coma structure, already behaving strangely from the moment we spotted it. The burst came from Sagittarius. Same region the backtracking analysis initially pointed to as origin for 3I Atlas, before the trajectory uncertainty made those calculations suspect. Same region where the WOW signal originated in 1977. 3 events, 3 different times, all connected to the same patch of sky. Is there a connection? Standard physics says no. Gamma-ray bursts are catastrophic events, massive stars collapsing, neutron stars merging, releasing enormous amounts of energy in seconds. But that energy disperses, spreads across the expanding sphere of the explosion. By the time radiation from a burst 5 billion light-years away reaches Earth, it's attenuated to levels that are detectable but not remotely strong enough to affect objects in our solar system. The flux from GRB 25072b at Earth's location was measured, bright by gamma-ray standards, strong enough to saturate some detectors, but in absolute terms, tiny, vastly weaker than the constant solar radiation bathing everything in the inner solar system. Not remotely sufficient to heat comets or trigger activity or cause detectable effects on small bodies. So no known mechanism connects the burst to the object, no physics that would make the timing meaningful. The correlation is either coincidence or indication of something we don't understand yet, some connection that operates through channels we haven't discovered, some influence that isn't mediated by electromagnetic radiation in ways our instruments detect, or coincidence. Universe is large, events happen constantly, some will align in timing purely by chance. Seeing patterns in random events is what human brains do. We're wired for pattern recognition, for finding meaning in noise, for connecting dots even when the dots aren't actually connected. But the mathematical timing of the burst pulses is itself unusual. The precise 4:1 ratio, the integer relationship. Natural astrophysical processes create pulses through rotation or oscillation or orbital mechanics. Those processes produce timing patterns, but usually not exact integer ratios. Not perfect mathematical relationships. There's noise, variation, messiness that comes from physical systems being complex and chaotic. Exact ratios suggest underlying simplicity, suggest relationships that are fundamental rather than emergent, suggest, though don't prove, that maybe the pulses were structured deliberately rather than being the random output of collapsing stellar material. And if the burst pulses were structured, if there was intention in the timing, then maybe the correlation with 3I Atlas's detection isn't coincidence. Maybe there's communication happening through channels we don't understand. Maybe the burst was a signal and the object is a response. Maybe they're both parts of something larger that we're only seeing fragments of. This is speculation piled on speculation, built from correlations that might be meaningless. But the correlations exist, the timing is precise, and dismissing it entirely because we can't explain it through known physics might be missing something important. Science advances by taking correlations seriously enough to investigate whether they're meaningful, by following patterns even when the connections aren't obvious, by being open to the possibility that what looks like coincidence might be causation through mechanisms we haven't identified yet, and by maintaining skepticism while investigating rather than declaring mysteries solved before the investigation is complete. The planetary alignment in January 2026 adds another timing correlation to the stack. Mercury, Venus, Mars, Jupiter, Saturn, Neptune, all within a 70-degree arc of sky. Tightest grouping in 89 years. Last occurrence in 1936. Rare configuration that creates gravitational influences on solar system bodies. The influences are small. Planetary perturbations on distant objects are weak compared to the Sun's dominant gravity, but they're real, measurable, can be calculated precisely and contribute to trajectory evolution over time. For 3I Atlas approaching Jupiter during this alignment, the combined gravitational pull from multiple planets might create subtle effects that aren't present in typical configurations. Does this matter? Does alignment influence the episodic thrust somehow? Unknown mechanism. No obvious connection. Planetary gravity affects trajectories through known equations that are already included in the models. Alignment doesn't add new physics. just concentrates existing gravitational influences in specific directions at specific times. But if there's something we don't understand about how the object responds to gravitational fields, if there are processes operating that aren't accounted for in standard trajectory calculations, then maybe alignment creates conditions that trigger or modulate those processes. Maybe the episodic thrust is somehow coupled to gravitational environment in ways we haven't recognized. Or maybe the timing is coincidence. Universe doesn't lack for events. Alignments happen. Objects pass through. Sometimes they occur simultaneously through pure chance without causal connection. Distinguishing between meaningful correlation and random coincidence requires mechanisms, requires identifying how one event could physically influence another, and those mechanisms are absent. So we're left with timing correlations that are interesting, that create patterns begging for explanation, but that don't have explanations grounded in established physics. Could be meaningful, could be noise, without mechanisms connecting them, without ways to test whether the correlations are causal, they remain provocative observations rather than actionable evidence. The solar maximum correlation is slightly more physically plausible because solar activity does affect comets in measurable ways. We're currently at the peak of the 11-year solar cycle. Sunspot numbers are high, coronal mass ejections are frequent, solar wind is enhanced and variable, all of which creates a more active radiation environment than during solar minimum. Comets respond to solar activity. Increased solar wind creates stronger forces on cometary plasma. Enhanced UV radiation drives more vigorous ionization in the coma. Coronal mass ejections can impact comets directly if the geometry aligns, creating sudden changes in the interaction with solar wind. We've observed these effects. They're real and documented. Could solar maximum activity trigger or modulate the episodic behavior of 3I Atlas? Possibly. If the object is sensitive to solar wind conditions in ways that typical comets aren't, if its internal processes respond to variations in the radiation environment, then the enhanced solar activity during maximum might influence the timing or intensity of thrust events. But solar activity varies on timescales from minutes to days. Sunspots rotate with the sun. Coronal holes create streams in the solar wind that sweep past objects as the sun rotates. If 3I Atlas were responding to solar activity, you'd expect its episodic behavior to correlate with these variations. Expect thrust events when solar wind is enhanced. Expect changes corresponding to coronal mass ejections passing by. And we don't see that correlation clearly. The episodic thrust seems to have its own rhythm that doesn't obviously match solar activity variations, doesn't synchronize with sunspot cycles or coronal hole transits or CME impacts. It's doing its own thing on timescales that might be influenced by solar conditions but aren't dominated by them. So solar maximum provides context but doesn't explain the behavior, might be contributing factor, might create conditions that allow or enhance the episodic processes, but isn't the primary driver, isn't the mechanism creating the thrust itself. All of these correlations, gamma ray burst, planetary alignment, solar maximum, create a sense that something unusual is happening, that multiple rare events are coinciding with 3I Atlas's passage, that the object's appearance and behavior are embedded in a larger context of unusual phenomena. But translating that sense into actual physics, into mechanisms that connect the pieces, remains elusive. We see patterns without understanding their meaning, observe correlations without identifying causation, and that's frustrating because science seeks mechanistic understanding, wants to know not just what happens, but why it happens and how the parts connect. Patterns without mechanisms are unsatisfying. Correlations without causation are provocative, but ultimately unfulfilling. We want explanation, not just description. Want to understand how the universe works, not just catalogue what it does. Maybe the mechanisms will emerge as more data accumulates. Maybe observations from the Jupiter encounter will reveal connections we're currently missing. Maybe the patterns will click into place once we understand what 3I Atlas actually is and how it operates. Or maybe the correlations are meaningless. Coincidences that we're over-interpreting because we want there to be meaning. Random events that happen to align without any deeper connection. Time will tell, observations will accumulate, and gradually the picture will either clarify into understanding or dissolve into acknowledged ignorance. Either outcome advances knowledge. Either way, we'll know more than we do now about what's real and what's illusion in the patterns we're seeing. The observation campaign for Jupiter is unprecedented in scope and coordination. Every major telescope network has scheduled time. Radio arrays are prepared to listen for electromagnetic emissions. X-ray observatories will be monitoring. Infrared instruments will track thermal signatures. Optical telescopes will document brightness and spectroscopic changes, all synchronized, all targeting the same object during the same window. And critically, amateur networks are mobilized, thousands of smaller telescopes, operated by enthusiasts who share data openly, who coordinate through forums and social media, who create distributed observation network that can't be controlled or censored by any single authority. This redundancy ensures that whatever happens at Jupiter will be documented from multiple independent perspectives, will be recorded by observers who aren't bound by institutional constraints or government classifications. If something dramatic occurs, if the object maneuvers or transmits or does anything that clearly indicates artificial origin, the amateur network will capture it, will share it globally within hours, will make suppression impossible through sheer volume of independent reporting. And if nothing dramatic occurs, if the encounter is routine and the object behaves exactly as outgassing comets should, the amateur data will confirm that too. Will verify that the strange behavior we've seen doesn't continue at Jupiter, will provide the observation that supports natural explanation. Either way, the distributed network ensures transparency, ensures that data is public and analysis is open, ensures that whatever conclusions emerge are grounded in observations that anyone can examine and verify. That's how science should work. That's how trust in scientific conclusions is built, through transparency and reproducibility and openness to verification. The professional observations will be more precise, will use larger telescopes with better instruments and more sophisticated analysis pipelines, will produce data that allows subtle effects to be detected and measured accurately. But the amateur network provides robustness, provides verification that the professional results aren't artifacts or errors or biased by preconceptions, provides independent confirmation that grounds extraordinary claims in ordinary observation, and the professional community is embracing this, is coordinating with amateur networks rather than viewing them as competitors, is sharing observation plans and encouraging distributed participation, is recognizing that thousands of eyes watching simultaneously is strength rather than weakness. That democracy of observation serves truth better than gatekeeping. This is the new model for major astronomical discoveries, not lone observatories making privileged observations, but networked collaboration involving professionals and amateurs, institutions and individuals coordinating globally to document phenomena that matter. And 3i Atlas is the test case, the event that shows whether this model can handle something of profound importance, whether distributed verification can maintain rigor while ensuring transparency. The answer will come in weeks. When Jupiter encounter happens and the network activates and the data flows, when we see whether coordination holds, whether data gets shared openly, whether analysis is transparent, whether conclusions emerge from consensus rather than from authority, whether the new model works as it should, or whether problems emerge that require refinement. And regardless of what the Jupiter observations show about 3i Atlas itself, the observation campaign will demonstrate whether science can evolve to handle discoveries in the age of distributed information and global communication, whether the old model of centralized control and delayed publication can give way to rapid sharing and collaborative analysis, whether transparency and speed can coexist with rigor and accuracy. These are questions that matter beyond this single object, that affect how science operates in the 21st century. that determine whether discovery serves public understanding or remains isolated in professional journals and institutional reports. And 3i Atlas, whatever it turns out to be, is forcing us to answer them. The trajectory prediction for Jupiter is complicated by the accumulated uncertainty from the episodic thrust. The closest approach distance is nominally 52 million kilometers, but the uncertainty cone has expanded so much that the actual distance could vary by millions of kilometers either direction, could be closer, could be farther. The geometry is uncertain because the current position is uncertain and the future trajectory is unpredictable. This affects planning, affects what observations are possible and what instrument settings are optimal. If the object passes closer than expected, some instruments might saturate. Light levels might be too high for sensitive detectors. Tracking rates might need adjustment. If it passes farther, signal might be weaker than anticipated. Exposure times might need to be longer. Pointing accuracy becomes more critical. So observers are preparing for a range of scenarios, multiple contingency plans, flexible scheduling that can adapt as the actual approach geometry becomes clearer, real-time coordination that allows rapid response if the object does something unexpected. This flexibility is necessary but adds complexity, makes the campaign harder to coordinate, increases chance of mistakes or missed observations, but it's also recognition of reality. Recognition that prediction has failed, and we're operating in a regime of uncertainty, where adaptation is more important than planning, where responding to what actually happens matters more than executing predetermined sequences, where science becomes more exploratory and less prescriptive. And that's appropriate for frontier research. For situations where we don't know what to expect, where the phenomena we're studying violate the frameworks we usually rely on, where flexibility and creativity matter as much as precision and planning, where being able to improvise becomes as important as following protocols. The Jupiter encounter will test whether we can do science in this mode, whether the community can adapt to unpredictability, whether coordination holds when predictions fail, whether we can gather meaningful data even when we can't forecast what we'll be observing. These are skills that matter for future discoveries, for handling phenomena that don't fit comfortable categories, for remaining effective when confronting genuine unknown. The question everyone wants answered is simple. What is 3i Atlas? And the answer, honest answer, after months of observation and analysis and debate, is that we don't know. Don't know with certainty. Can't determine definitively from available data whether it's exotic natural object or something else entirely. Can't distinguish between competing hypotheses with confidence that would satisfy scientific standards. We know what it's doing, know it's executing episodic thrust that creates trajectory deviations, know it's releasing narrow size distribution of dust particles, know it's showing synchronized pulses across multiple wavelengths, know it's maintaining structural stability despite activity levels that should tear it apart. Know all these things through careful measurement and analysis. But knowing what it does doesn't tell us what it is, doesn't reveal whether the behaviors come from natural processes we don't understand or from designed systems operating according to purpose. Both explanations accommodate the observations. Both can be made to fit the data with appropriate adjustments and assumptions. Neither is clearly superior based solely on what we can currently measure. The natural explanation requires stacking special circumstances, unusual composition, exotic internal structure, atypical formation conditions, specific sublimation dynamics, each individually plausible, together creating scenario that feels contrived. That requires many things to be true that we can't verify. That builds model from assumptions rather than observations. The artificial explanation requires accepting that intelligence exists beyond Earth, that civilizations build things and send them through space, that we're being visited, or at least that objects designed by other minds pass through our solar system, each conceptually challenging. Together, creating scenario that violates comfortable assumptions about our uniqueness and our isolation. Which explanation requires more extraordinary assumptions? Depends on your priors. on what you believed before examining this particular object. If you think life is common and intelligence frequent, artificial origin isn't particularly extraordinary. If you think we're rare or unique, natural explanation feels safer regardless of how many special circumstances it requires. Science is supposed to be objective, data-driven, free from prior beliefs. But in practice, especially when data is ambiguous, priors matter enormously, shape how we weight evidence, affect which explanations we find compelling, determine thresholds for accepting unconventional conclusions. And there's no purely objective way to set those priors, no equation that tells you how probable extraterrestrial intelligence is, no observation that determines whether technological civilizations are common or vanishingly rare. You're left with philosophical intuitions masquerading as scientific probabilities, with beliefs about the universe's fundamentals affecting how you interpret specific observations. This is uncomfortable, but honest acknowledgement of how scientific reasoning actually works when you're at the edge of knowledge, where data constrains but doesn't determine conclusions, where interpretation depends on frameworks that themselves aren't fully grounded in observation, where being right requires not just analyzing data correctly, but choosing the right priors to start from. And different researchers choose differently, have different intuitions about what's probable, reach different conclusions from the same observations. That's not failure. That's what frontier science looks like. Debate, uncertainty, competing interpretations, gradual convergence as more data arrives and as frameworks get tested against predictions they make. We're in that uncertain phase with 3i Atlas. Before convergence, before enough evidence has accumulated to force consensus, multiple viable interpretations, debate that's productive but unresolved, questions that matter but that can't yet be answered definitively. And Jupiter might help, might provide observations that tip the balance, might create evidence that clearly favors one interpretation over others, or might just add more data to ambiguous pile, might deepen mystery rather than resolving it, might leave us with better understanding of what the object does without clarifying what it is. Either outcome represents progress. Either way we learn. Either way our knowledge increases even if our certainty doesn't. And that's what science is actually about. Not achieving certainty, but increasing understanding, narrowing uncertainty, building models that better capture reality even when reality resists being fully captured. The continuation of episodic thrust behavior is itself a conclusion, a result, a finding that matters regardless of what's causing it, because we now know that interstellar visitors can exhibit this kind of behavior, that objects arriving from beyond can maneuver, or at least appear to maneuver. That trajectory prediction can fail not because our physics is wrong, but because the objects don't follow purely gravitational paths. This changes how we'll approach future interstellar visitors, changes observation strategies, changes what measurements we'll prioritize, changes expectations about what's possible and what's normal. Whether 3i Atlas is natural or artificial, it's expanded our understanding of what interstellar objects can do, has shown us behaviors we hadn't seen before, has challenged models we thought were adequate. And that expansion is valuable, makes us better prepared for the next visitor, better equipped to recognize whether it's behaving normally or anomalously, better able to design observation campaigns that capture the right data, better positioned to interpret what we're seeing because we've now seen more of the range of possibilities. The dataset we're building will be studied for decades, will be analyzed and reanalyzed as techniques improve, will be compared against observations of future visitors to see whether 3i Atlas's behavior was unique or representative, will contribute to our understanding of how planetary systems form and evolve and eject material that then wanders the galaxy. Regardless of the resolution to the natural versus artificial question, that contribution is lasting. Is the scientific return on the months of observation and analysis? Is knowledge that persists even if some questions remain unanswered? Is progress even amidst uncertainty? The journey of 3I Atlas through our solar system is nearly complete. Closest approach to Earth happened. Jupiter encounter is approaching. After that, the object heads outward beyond all planets into the sparse region between solar system and interstellar space. Will fade as distance increases, will drop below detection thresholds within months or at most a couple years, will disappear from our instruments carrying its secrets with it into the dark. We'll be left with data, terabytes of observations, images and spectra and photometry and trajectory measurements, all archived, all available for future analysis, all waiting for someone to find the pattern we missed or apply the technique we didn't think of or make the connection we couldn't see. And we'll be left with questions about what we actually saw, about what it means, about whether we missed opportunity to gather critical data or asked the wrong questions or focused on wrong measurements. Second guessing is inevitable. Hindsight will reveal mistakes we made, things we should have done differently, observations we should have prioritized. But we did what we could with the understanding we had, made decisions based on available knowledge, adapted as new data arrived, responded to anomalies as they emerged. That's all anyone can do when confronting genuine unknown, when studying something that doesn't fit existing categories and that challenges frameworks you're using to interpret it. The object is still there, still moving, still executing thrust events on schedule we can't predict, still defying our models, still being strange in ways that demand explanation even as explanations remain elusive. And in a few weeks it reaches Jupiter, where the next chapter of this story unfolds, where observations might clarify or confound, where answers might emerge or questions might multiply, and we'll be watching. Professional and amateur alike, institutions and individuals, coordinated and distributed, all eyes on the same object at the same moment, all gathering data that will be shared and analysed and debated, all participating in discovery regardless of what the discovery turns out to be, because that's what matters ultimately, not whether we solve the mystery immediately, but whether we engage with it honestly, whether we gather data rigorously, whether we analyse carefully, whether we remain open to possibilities even when they're uncomfortable, whether we let evidence guide conclusions rather than forcing conclusions onto evidence. 3I Atlas is teaching us these lessons, is forcing us to confront our assumptions, is showing us where our models break and our predictions fail, is making us better scientists through the discomfort of encountering something that resists easy explanation. And whether it's a comet unlike any we've seen before, or whether it's something else entirely, something that shouldn't exist according to our current understanding, it's expanding what we know is possible. It's showing us the universe is stranger than our theories predicted. It's revealing that interstellar space isn't empty of surprises, but full of phenomena we're only beginning to encounter. The visitor came. The visitor challenged us. And the visitor is leaving, carrying forward into the galaxy whatever secrets it holds. We had our moment, had our chance to observe and measure and analyze, had our opportunity to understand if we could. Whether we succeeded, whether we figured out what we were actually looking at remains uncertain. The data exists. The analyses continue. The debates persist. And time will tell whether the patterns we're seeing are real or imagined, whether the anomalies are evidence of something profound or just complications in an unusual but natural object. But we tried. We observed carefully. We measured precisely. We thought deeply. We debated honestly. We remained open to possibilities. We followed the data wherever it led, even when it led to uncomfortable questions. And that's enough. That's what science requires. Not certainty, not immediate answers, just honest engagement with reality as we observe it. Just willingness to revise understanding when observations demand it. just commitment to following evidence even when it points toward conclusions we weren't expecting. 3i Atlas, whatever you are, wherever you came from, wherever you're going, thank you for the challenge. Thank you for the mystery. Thank you for forcing us to question our assumptions and test our theories and confront the limits of our understanding. The object speeds on. The distance grows. The observations continue. And humanity watches, curious and confused and excited and uncertain, as an interstellar visitor demonstrates that the universe still holds surprises we're not prepared for, and that the cosmos is far stranger and possibly far more populated than comfortable assumptions would have us believe. The journey continues, the questions remain, and the search for answers, honest search grounded in observation and constrained by evidence and open to revision, defines us as a species that looks up and wonders and tries to understand even when understanding proves elusive. Breaking physics, defying prediction, challenging frameworks, and forcing us to grow. That's the legacy of 3i Atlas, regardless of what it ultimately turns out to be. And that legacy matters more than any single answer to any single question about natural versus artificial origin. The universe is speaking. We're learning to listen. And the conversation has only just begun.